I'm Professor Rad, and this is Precalc video 324, solving trig equations using trig identities. So in this video, we will be building on our techniques from the last video, where we solved some basic trig equations. So now we're going to apply those techniques and broaden our horizons, I guess, or apply advanced techniques to solving equations as well. So we're going to solve two equations in this video, and the first one's on the board for us. So we're going to solve the equation cotangent squared theta is equal to 3/2 cosecant theta. Now, when I look at an equation like this one, a few things I'm noticing. So thing number one that I'm noticing is that I don't have a specified domain that I'm looking for my solutions on. So that means this is going to require a general solution. So that means at the end, I'm going to have to take my base solutions and add k times whatever the period is. The second thing that I'm noticing is that I have two trig functions. I have cotangent and I have cosecant, and that is not so good. Ideally, you want to have just one trig function in your equation. So this is where those properties are going to come into play. So we're going to use some trig properties to rewrite this in terms of either just cotangent or just cosecant. So this is going to become one of those things that you have to train your eye to see to know what property is going to work best. So what my eye is seeing is this cotangent squared here. So if you have one of the trig expressions being squared, that's a good indicator that you want to use a Pythagorean identity. So we do have a Pythagorean identity that involves cotangent, and that's going to be that's going to be cotangent squared theta. I had to think about it for a minute. Plus 1 is equal to cosecant squared theta. So we have this identity that involves cotangent squared, and it involves cosecant squared, which is good news for us because the other trig function involved here is cosecant. So this is a good identity for us to use. The only problem is that I now need to replace cotangent squared theta with something. So I'm going to take this identity and I'm going to subtract 1, and that will solve for cosecant, or sorry, will solve for cotangent squared. So when I subtract 1, I'm going to get cotangent squared theta is equal to -1 plus cosecant squared theta. So now, where I had cotangent squared initially, I can replace that with -1 plus cosecant squared theta. So I'm going to rewrite this equation as -1 plus cosecant squared theta is equal to 3/2 cosecant theta. So that's sort of the first layer, the first stage for this problem, is rewriting it so that we have the same trig function throughout the equation. We only have one trig function to worry about. Now, let's get everything over to one side, because I noticed that I have a trig function being squared, which is a good indication that this is going to be quadratic in form. So I'm going to bring this 3/2 cosecant theta over to the side as well. And I'm going to rewrite it so I have cosecant squared theta first. Then when I subtract this, I'm going to get -3/2 cosecant theta. Then I have -1, and that's equal to 0. So what I'm seeing is something squared minus something minus a constant equals to 0. So this is essentially a quadratic equation. It would be as if I had x squared minus 3/2 x minus 1. So if it helps you to think of this in terms of x, you could replace the cosecant theta with x and solve it that way. But I'm going to go ahead and continue using cosecant here, just so we can kind of get a sense for what that's going to look and feel like. Now, when I'm solving a quadratic, I like to factor if I can. So what I'm going to do is I'm going to multiply through by 2 to eliminate this fraction, and that will help me to factor. So I'm going to multiply everything by 2, and that will give me 2 cosecant squared theta minus 3 cosecant theta minus 2 is equal to 0. And now I'm going to need two numbers that multiply to a -4, but add to this -3. So I'm thinking -4 and a +1 ought to do the trick. So I can rewrite this middle term. We have 2 cosecant squared theta, and I'm going to rewrite the middle term as -4 cosecant theta plus 1 cosecant theta, because that'll give me that -3, minus 2 is equal to 0. And now we can factor by grouping. So from these first two terms, we have a 2 and a cosecant in common. So I'm going to factor that out. And that will leave me with a cosecant minus 2. There's nothing in common here, so I'm just going to write it as a 1. And so now these two have a cosecant theta minus 2 in common. So I'm going to factor that out. And the other factor will be 2 cosecant theta plus 1. All right, so now we have a product equal to 0. So we can apply the 0 property to solve for at least cosecant of theta. So let's see if I can squeeze that in over here. So we have cosecant of theta minus 2 equals 0. So that's from this first one. So that means that cosecant of theta is going to equal 2. And then we have from the second factor, 2 cosecant theta plus 1 equals 0, which means 2 cosecant of theta is -1. So cosecant of theta is -1/2. Okay, so we've now solved 2 equations for cosecant of theta, which means we're on the right track. We're almost getting to our solution. We do have a problem with one of these, however. So this first equation is totally fine. The second one is a little bit suspicious. And it's suspicious because cosecant can't be between -1 and 1. Remember when we graphed cosecant, it was like those series of U's on the top and on bottom. So cosecant can only give us a value that's between -1 and -infinity, or +1 and +infinity. So this can't happen. So we're going to reject this equation. It's not going to give us any solutions. And we're going to focus our attention up here on this equation. So I think I need a little bit more space. So I'm going to erase this quadratic that we solved. And I'm going to keep this over here for reference. So now we have cosecant of theta is equal to 2. Now, if you can remember stuff in terms of cosecant, that's fantastic. If you have trouble, remember that cosecant is a reciprocal of sine. So if it's easier for you to think in terms of sine values, we can go ahead and write this in terms of sine. So the reciprocal of cosecant is sine, and the reciprocal of 2 is 1/2. So what we're looking for are all the thetas, all the angles, for which sine of that angle will give us 1/2. So let's sketch out a unit circle. See if we can find some solutions. So sine is 1/2. That means the y value is 1/2. So that means we're going to be here and here. Oh, that looks like a little face where the eyes are connected with a smile. Okay, anyway, so we have our unit circle to look at. And this point is happening at pi/6. And then this one is just 1/6 away from pi. So that must be 5pi/6. So because we have 2 possible situations, where we can equal 1/2. That means when we go to write our general solution, we have to use both of those as kind of our starting points. Now, when we are solving this, we were looking at an equation that I've since erased, but our equation was written in terms of cosecant. So the period of cosecant is going to be 2 pi. So putting all of that together, we get solutions that are going to be 5 pi over 6 plus 2k pi, or pi over 6 plus 2k pi, where k is an integer. So this is going to be our inelegant yet still correct solution for this equation. Now, if you wanted to make this a little bit fancier, you could go ahead and look for patterns. So you could plug in values for k to see if we have any redundancies here or if there's a tighter way of writing this solution. But for purposes of this video, I want the focus to be on solving using trig identities, and I will accept solutions that look like this. So this is where we're going to stop on this one. All right, let's take a look at a second example that will require trig identities to solve. All righty, so for our second example, I have good news for us. This is going to be a definite equation. So what we mean by that is that we have a definite domain for our solutions, unlike the last example where we were solving for in general. So in general is when you're going to have to add k multiples of the period to your base solutions. When we have a specific domain, so in this case we have a definite domain of -pi to 3 pi, then we're just going to list out the individual solutions we get. The other bit of good news for this one is that if we look at our equation, we've got cosine and cosine and no other trig functions. So we don't have to worry about using a Pythagorean identity to rewrite, sine in terms of cosine or something like that. However, bit of bad news here. And the bad news is that even though we have 2 cosine functions, their arguments are not the same. So it turns out this one is not going to be super easy in terms of just combining them into one cosine, because we have cosine of 2 phi here, and this one we only have 1 phi. So what we're going to need to do is still apply a trig property to write this in terms of just cosine of phi. So we're going to keep this cosine phi alone, and we want to rewrite this one so that it's just in terms of cosine, if at all possible. So for our double angle formulas, when we had twice an angle in here, we actually had 3 double angle formulas for cosine. So we had cosine squared minus sine squared. We had 1 minus 2 sine squared phi, or we have 2 cosine squared phi minus 1. So we have 3 options to choose from when we use this cosine double angle formula. So in this case, I'm probably going to go with this third option, because this third option only involves one trig function, and it involves cosine, which we have. We already have cosine, so we're going to use this one here. If, for example, I had sine of phi here instead, then I would have gone with the second option. And then, if I had like plus sine squared phi off on the end here, I might use this one because that would eliminate the sine squared component. So you want to look at the other components to your equation to help you decide which of these double angle formulas to use if you have cosine of 2 phi. So because we just have cosine, we're going to use this one. And I'm going to rewrite cosine of 2 phi as 2 cos squared phi minus 1. So this equation is going to become 2 cosine squared phi minus 1 plus 5 cosine of phi plus 3 is equal to 0. So now this is very similar to the last example, actually, where we had cosecant squared and then cosecant. Now we have cosine squared and then cosine. So I'm going to show you that we could do kind of like a little substitution here and rewrite cosine squared phi and cosine phi as like an x. So if that helps you envision these problems a little bit more easily, you can go ahead and do that. So, ooh, squeaky top here. I could think of this piece as x squared, and I could think of this piece as x. And then everything else I'm just going to bring down. So we have a 2 minus 1 plus 5 plus 3 equals 0. So if I rearrange this, this is going to give me 2x squared plus 5x. 3 minus 1 is 2 equals 0. And then we can go ahead and factor that. Or if you wish, you can use the quadratic formula. That's also totally fine. I'm going to keep my x's in red, however, to remind me that I'm not ultimately solving for x. I want to figure out what this phi is ultimately. So let's use the quadratic formula for this one. So let's say we've got x is equal to negative b. So negative 5 plus or minus the square root of b squared, so 25, minus 4ac. So 4 times 2 is 8, times 2 is 16, all over 2a. So 2 times 2 is 4. So this is going to give us negative 5 plus or minus the square root of 9 over 4. So that will give us negative 5 plus or minus 3 over 4. So let's see, if I do negative 5 plus 3, that gives me a negative 2. So that will give me a negative, write that over here, negative 2/4, which is a negative 1/2. And if I do negative 5 minus 3, that will give me a negative 8. So I get negative 8 over 4, which is a negative 2. All right, so you can use the quadratic formula to solve for this. This one also would have factored since we got rational solutions. Now remember, we're not done. These are values for x, and that's nice, but ultimately we want values for phi. So x was a stand-in for cosine of phi. So I can rewrite this so that I have cosine of phi is negative 1/2. So let me write that up here. Cosine of phi is negative 1/2. And from this one, we have cosine of phi is negative 2. So we have more work to do, but we at least have a much simpler looking thing for us to review than this beast here. So I'm going to keep this up here so that we have something to reference. And one of these equations should be turning your hearts to ice because it doesn't make sense. And that's the second equation here. Remember that cosine is always going to spit out a value between negative 1 and 1. So we can't have cosine equal to negative 2. That's just silly. So we're going to reject that solution. And we just have cosine is equal to negative 1/2. So we're looking for all values of phi so that cosine of phi is equal to negative 1/2 on this interval from negative pi to 3 pi. All right, so let's draw a unit circle to help us out here. Now for cosine to be a negative, that means we have to be in quadrants 2 and 3. And cosine is negative 1/2, so that means we're going to be up here or down here. And these are at the pi thirds. So I'm going to indicate my pi thirds to help me count. So this would be no pi thirds, 1 pi thirds, 2 pi thirds, 3, 4, 5, and then 6 pi thirds going around. And our domain that we're looking at goes from negative pi to 3 pi. So I'm going to do the negative swirl first. So I'm going to go from 0 to negative pi. So from 0 to negative pi, we're going to hit this solution once. And then we have 3 pi. So this is going to be from 0, 1 pi, 2 pi, 3 pi. So on that swirl, I hit 1, 2, 3. And then we're done. So it looks like all told, we're going to get 4 angles for our solution here. So we have 4 solutions to this equation. So let's list them in numerical order. So we'll do the negative one first. So that's going to be negative 1, 2. So we have negative 2 pi over 3. Then in the positive direction, we're going to have 1, 2. So we have 2 pi over 3. 3, 4. 5, 6, 7, 8. There we go. Those are going to be our solutions to the equation. Now, of course, if you wanted to check your solutions, you could substitute these in for phi, and you should get 0 in the end. So that's going to wrap up this video on using trig identities to help us solve equations. Now, I did want to sneak in a little bit of substitution into this video as a tiny preview as to what's to come in the next one. So sometimes if the trig function piece is getting in the way, it might be easier to simplify it down a little bit. So like in this second example, we replaced cosine of phi with x, and then we had to go back in terms of phi at the end. So that's one type of substitution that's common in both this course and also in calculus. So sometimes if you have something that's really complicated, it can cause you to lose sight of the bigger picture. So in our next video, we're going to be looking at some other instances when substitution might prove helpful. So I'm looking forward to seeing you then. In the meantime, I hope you found this video helpful, and I hope you have a fantastic day. Bye for now.